Meteorological Training Institute for delivering lecture in virtual lecture series. Dear participants, Ms. Monika Sharma Madam is the speaker of today's first lecture. So I request Shri G.K. Sawai Sarja sir to kindly introduce Ms. Monika Sharma Madam to the participant.
Thank you, Chetna Madam. I am very happy to introduce our colleague, Dr. Monika Sharma. She is a scientist in India Meteorological Department with MSc in Physics from Delhi University. She joined IMD in 1997. She has an experience of 12 years in tropical cyclones monitoring and forecasting. She has made significant contributions in improvement of early warning services of tropical cyclones to 13 WMO ESCAP panel member countries, including India, and severe weather monitoring and forecasting to 9 countries of South Asia under WMO's severe weather forecasting program. She also contributed in research publication preliminary reports of cyclones. She has been nominated as vice chair of WMO advisory group on severe weather forecasting in June 2022. She is a member of WMO's Regional Association 2 and rapporteur for preparation of tropical cyclone operational plan since 2020. She was awarded Best Employee of IMD in 2014 for her contributions in improvement of cyclone warning services. She received appreciations from Director General of Meteorology IMD for her contributions during monitoring of cyclones Falin, Hudud, Fani, Amphan, and WMO for organizing WMO's tropical cyclone forecasting training in 2022. Her topic is Basics of Science of Cyclone. I now request Madam to continue her lecture. Thank you. And the participants can ask questions after the lecture. In chat box also they can mention the question. Feel free to ask questions. Thank you, Madam.
Thank you, sir. First of all, I want to thank DGM IMD and Head MTI Pune, Dr. Somnath Datta, for providing me this opportunity. And I welcome all the participants to this lecture series. And I'll be discussing about the basics of cyclones today with you. So in my presentation, I have put some popular questions also, that is just for your reference so that you remember them. I'll be discussing them, and after this lecture, we may discuss your questions. So I'm sharing my screen. So, my screen is visible to all?
Yes, ma'am. Yes.
Okay. So we'll be discussing about the basics of tropical cyclones over North Indian Ocean today. And basically, I'll be covering briefly about I'll be discussing few facts about cyclones, then climatology of cyclones, structure of tropical cyclones, including the horizontal, vertical, and thermal structure, then various theories of formation of tropical cyclones, then movement of TCs, various parameters that are responsible for cyclogenesis and intensification, then impact of climate change on various features associated with cyclones, then what is the basic monitoring and forecasting process with cyclones, and cyclone warning services of IMD is a success story that also we'll share with you briefly. So, if you consider the damage associated with cyclones, then about one third of the hydrometeorological disasters are caused by tropical cyclones, and this is based on a study by WMO for the period during 1970 to 2019. And if you see, 7 out of 10 disasters that caused biggest economic losses, that they were associated with TCs, and our region particularly is has witnessed some of the notorious some of the severest cyclones, and during 1917 Bangladesh about 3 lakh people died due to tropical cyclones. And in India also, in 1971, we witnessed death toll amounting to about 10,000 in Andhra Pradesh. And then in 1999 super cyclone, about 10,000 casualties were observed. But today, if you see, with careful planning and with utilization of various modern means and technologies, the death toll due to cyclones has been reduced to less than 100 during last 100 years. So that we'll discuss with you today. So, cyclone, if you see, is a multi-hazard event, and it brings with it heavy torrential rains, strong winds, and storm surge. And if you see, storm surge among all these associated weather events is the biggest killer. It causes flooding of coastal areas, erosion of beaches, and soil fertility is lost for years, and it also causes damage to structure. Similarly, if you see winds cause losses to the structure, injuries to human, and injuries to livestock. Then similarly, the rain-induced floodings, they cause land subsidence, flooding, and contamination of water supply. Apart from this, cyclones are also associated with various secondary hazards, like we have observed landslides also. Sometimes tornadoes are also observed with cyclones. But if you consider among all these, storm surge is the biggest killer. It is the most disastrous weather event associated with a cyclone. And if you consider the classification of tropical cyclones over North Indian Ocean, then based upon the intensity, various categories have been fixed, and starting from a low pressure area or well marked low pressure area, when the intensity is less than 17 knots, we call when the system intensifies and associated maximum sustained wind speed is between 17 to 27 knots, then it is characterized as depression. As the system goes on organizing and intensity goes on increasing, the various categories are described as deep depression, cyclonic storm, severe cyclonic storm, very severe cyclonic storm, then extremely severe cyclonic storm. This category was introduced in 2015 for the winds ranging in the category of 90 to 119 knots. And then super cyclonic storm, it has maximum sustained wind speed more than or equal to 120 knots. So this is the nomenclature that is utilized over the North Indian Ocean region by IMD. Then, if you consider the definition, then cyclones are basically the low pressure systems in which the winds they rotate in anti-clockwise direction in the northern hemisphere, and the associated maximum sustained wind speed associated with the system is 34 knots. And cyclones are synoptic scale systems. Average size is more than 100 kilometers, and they are the non-frontal systems. They develop over the warm sea area in the tropical region, and they are, if you see this image on the right hand side, this is the image from Karaikal radar, and you see that the clouds associated with the cyclones, they are organized in a definite pattern. And cyclones over different regions, they are called by different names. नहीं चाहिए, चलेगा. They are called by different names, and over the West Pacific, they are named as typhoons. Over Australian region, they are willy willies, and over the Indian seas, we call them tropical cyclones or cyclones, and over Atlantic and Eastern Pacific, they are named as hurricanes. And Henry Beddington is the person who coined the term cyclone, and to him, the cyclone, it appeared like the coil of the snake, and so he named it as cyclones. If you consider the climatology of tropical cyclones, then globally, if you see our region, we witness formation of around 5 cyclones over the North Indian Ocean, with 4 over the Bay of Bengal and 1 over the Arabian Sea. And out of these 5, 3 intensify into severe category storms, and the most frequent is the Northwest Pacific region, where we have about 26 tropical storms with 16 intensifying into severe category. And in over the North Indian Ocean also, year to year variation may be there. We may have one cyclone, or we have witnessed about 10 cyclones also in a year. So these are particular years where we witnessed 10 cyclones: 1893, 1926, 1930, and 1976. If you see the figure, this left hand side figure below, then you can see that Bay of Bengal is the region where we are having more cyclones as compared to the Arabian Sea. And the reason is that Bay of Bengal is comparatively warmer as compared to the Arabian Sea. Sea surface temperature over Bay is higher as compared to that over Arabian Sea. And also the bathymetry, this bay has conical shape. The bathymetry is like that. Here we have frequent development of cyclonic circulations, and also bay region is adjacent to Northwest Pacific. We have remnants from South China Sea entering into Bay of Bengal, and these remnants also intensify into cyclonic storms. So these are some of the reasons because of which Bay has more frequent cyclones as compared to Arabian Sea. And if you consider the rate of dissipation, then over the Arabian Sea it is about 56%, and over the Bay of Bengal the rate of dissipation is very less, about 16%. And mainly because the bay is warmer as compared to Arabian Sea, and also over the Arabian Sea you have dry cold air entrainment from the Arabian Peninsula region, and wind shear also is comparatively higher. Then coming to the hazard proneness, this hazard proneness. If you see, almost all the districts of India, they are prone to disaster due to cyclones. But if we compare the east coast and the west coast, then east coast is more prone as compared to the west coast, and that is mainly because here more genesis is taking place, and also because cyclones normally have the tendency to move northwestwards. Sorry, cyclones have the tendency to move northwestwards, and the cyclones that originate over the Arabian Sea, normally they originate over the east central Arabian Sea, and they have the tendency to move northwestwards. So they generally move towards the Arabian Peninsula region. And if at all, due to some reason, they recurve, then they recurve towards the Gujarat and the Maharashtra coast. So just look at here, the Kerala, Karnataka coast, they are more or less safe. They are comparatively less prone to the disaster due to the cyclones. And the most vulnerable states are the West Bengal, the Odisha, and the Andhra Pradesh coasts. And this hazard proneness has been categorized based upon the frequency, the intensity, the wind strength, the probable maximum precipitation over these districts, and the probable maximum storm surge observed. Then coming to the structure, horizontally, if you see, a cyclone is a synoptic scale system, and it has the dimensions of about 100 to 1000 kilometers, and vertically it extends up to 15 kilometers. And the average speed of the storm with which it moves is about 14 to 15 kilometer per hour, or about 300 kilometer. It covers a distance of about 300 kilometers in a day. And if you consider the various parts, then we have the central part of the storm, that is called the eye. And it is the region where we do not find any cloud. This is the region where no winds are observed, no weather is observed, and normally the size of the eye is about 10 to 100 kilometers. And how eye formation takes place, that I'll discuss in next slides. and time being you understand that this is the region where no clouds are seen, and so eye kind of structure appears here. And when eye passes over a region, then there is abrupt cessation of weather precipitation over that area. And the shape of the eye, it may be circular or elliptical, it may be a closed eye or an open eye. And you should remember that eye is a region which is comparatively warmer as compared to its surroundings, and this is the region where minimum pressure is observed and the winds are calm over this region. Then is the region you see this the next is the eye wall region. It is the most disastrous part of the storm, and this is the region where intense rain bands they spiral inwards, and this is the region where most intense winds are observed, most severe weather is observed. And next comes the if you see this figure, the figure on the right, this is the microwave imagery. So the red colored ring is your eye wall region, and this blue is your eye, the central calm region. And then you have spiral bands, the cloud bands spiraling inwards. And these spiral bands, they are normally 5 to 50 kilometers wide and 100 to 300 kilometers long. And then you have the outer storm bands, and as you move away from the center of the storm, the wind speed decreases, the rains also decrease. And when the system is approaching, then it is the eye wall region that brings the most disastrous weather, and when eye passes over a region, then no weather is observed. And after passage of eye, again you will have because the rear end of the eye wall will be passing through that area, again strong intense winds and intense rainfall will be observed. Next comes the vertical structure. So vertically, it extends up to about 10 to 15 kilometers. And if you consider, it is divided, it can be divided into three layers as inflow layer, middle layer, and the outflow layer. The inflow layer, it extends up to a height of about 300 kilometers, up to 700 HPA. And within the inflow layer you have strong inflow you see here strong cyclonic circulation winds entering into the core of the system. And within the inflow layer, the diameter of TC, it remains the same, and it is more or less symmetric near the core, and it is asymmetric as you move outwards. And then your middle layer, it extends from 700 to 400 HPA layer. And in the middle layer, the inflow is not that strong, and the diameter, if you see this figure, the figure at the bottom, then diameter of this tropical cyclone is gradually decreasing. Then in the middle layer also there is sharp decrease in the diameter with height. And in the outflow layer, it is about the diameter is about 100 kilometers. And you see the figure on the top. In the outflow layer, there is outflow of winds, and these winds descends away from the center of the storm. And in case of intense systems, what happens is these winds, they some of these winds, they also enter into the core of the system, and they subside downwards. And as a result of this subsidence, the pressure at the core of the system further falls. And also because of this subsidence, the core of the cyclone is warm. Next comes the structure, TC structure. This I have already discussed with you, that we have in the inflow layer, we have the winds moving towards the core of the system. And then you have the updrafts in the wall cloud region. And then in the upper levels, outflow is taking place, and these outward moving winds, they are subsiding away from the center of the storm, and some of these winds, they are subsiding inwards into the core of the storm. that leads to the intensification of the system and also leads to the warm core of the system. Next comes the TC circulations. If you see the how the various kind of forces are balancing each other, then within the eye wall region, if you see, you have a balance between the pressure gradient force and the Coriolis and centrifugal force. They are acting outwards, away from the center, and you have high pressure. You have low pressure in the core of the system, and high pressure is outside, so you have pressure gradient force directed towards the center of the storm, and there is balance occurring between the pressure gradient and the Coriolis and centrifugal force. But because of friction, what happens is friction tends to reduce the velocity, and as a result the Coriolis force and centrifugal force, they are also reduced. This thus friction tends to create an imbalance between the pressure gradient force and the Coriolis and centrifugal force, and as a result the winds, they turn inwards towards the core of the system. So this is about the circulation, and within the eye region, because there is not much of Coriolis force there, the eye diameter is very less. There is balance between the pressure gradient and the centrifugal force only. Next comes the thermal structure of the tropical cyclone. So this, if you see, the core of the tropical cyclone is warmer as compared to the outside temperature, and as the winds are rising upwards, you know that they are cooling, condensing, and latent heat of condensation is released, and this release is the maximum at 300 HPA levels. That is, this warm temperature anomaly is observed maximum at 300 HPA levels, and this warm core is responsible for extremely low pressures at the center of the storm at surface. And the reason why, because of why you have a slanting eye wall in the higher levels, is that as you move upwards, the winds, they tend to decrease, and because angular momentum is conserved, mvr has to remain constant, so r will increase, and this will lead to the expansion. If you see, the eye is expanding as you are moving upwards towards the troposphere, and the eye wall is also, it is slanting outwards. Next comes how eye develops. So for development of eye, it is basically because of the conservation of angular momentum, and the subsidence that we observe in the core region, that eye develops. And you know that when the spin eye is seen when the system, when in case of severe cyclonic storm and above category storms, we do not observe eye in case of depressions, deep depressions, and normal cyclonic storms. And when the wind speed is very high, then at the surface, what happens is a kind of vacuum is generated, and as the at the core we have a kind of vacuum, and in the eye wall region, the winds, their updraft is seen, and you know that there is divergence in the upper levels, and the winds are diverging, moving outwards. But some of the winds, because there is a vacuum kind of situation in the core, some of the winds, they tend to move towards the core, and these winds, they subside downwards, and as a result of this subsidence, the core becomes and subsidence, you see, evaporation, the rising motion, it leads to formation of clouds. And if you observe subsidence or descending motion in a region, then that means there will be no cloud formation. That this is the region that will be clear, or clear sky will be seen, and no weather will be observed, and this is called eye. and because of subsidence, this region is warmer as compared to its surroundings, and because of this subsidence, the pressure at the surface falls further, and this leads to further intensification of the storm. Next comes, but it is not that always we have one eye and one eye wall. Sometimes we have double eye wall also, and double eye is also observed. And in case of very intense systems, normally when in case of extremely severe cyclonic storms and above category systems, the outer spiral bands, what happens is, just a minute, these outer spiral bands, they start organizing, and gradually they organize, and what happens is the supply of energy and moisture to the inner eye wall, and the inner eye is completely snapped, and these outer storm bands, they start organizing themselves, and they form a secondary eye wall. And because now there is no supply of energy and moisture to the inner core, the inner eye wall, the primary eye wall, it starts collapsing, and the outer eye wall, it starts organizing. So gradually this collapses, and this is known as eye wall replacement cycle. And during the process, the size of the eye also increases, and increase in size of eye is an indication of momentary weakening of the system, and further the system will intensify or weaken. That will depend upon the various environmental features. So if the system enters into an environment that is favorable for intensification, then it will intensify. Otherwise, the eye wall replacement cycle and the formation of secondary eye wall, it leads to weakening of the system. Next comes the relationship between the pressure drop at the center and the maximum sustained wind speed. Fletcher's gave a formula over Atlantic for the for maximum sustained wind speed and the pressure drop, and as per Fletcher's formula, Vmax is 16 into under root of delta P, where delta P is the difference in the pressure of the outermost closed isobar and the central pressure. But over our region, applying certain corrections and certain approximations, and here we assume that like Mishra and Gupta, they gave this formula, and they made certain assumptions that there is cyclostrophic wind approximation over the Indian seas, and they found that Vmax is 14.2 into under root of delta P. Actually, Fletcher's formula is 16 into Vmax equal to 16 into under root delta P, but that is valid for the Atlantic, and this formula is valid for the North Indian Ocean. Next comes how the formation, how a system is developing. So for development of a tropical cyclone, we say that there should be conditional instability of second kind, and by that we mean that instability in the atmosphere means that the lapse rate should be such that when the parcel of air it is rising upwards, it should cool. And if it is in case of conditional instability of second kind, we also have a condition that there should be relative humidity more than 50% up to the middle levels. And this relative humidity, it helps when the air is the rising air, when it cools, it condenses, latent heat of condensation is released, and it warms the environment in its vicinity. And if moisture is available, then that it will further evaporate, and as a result further latent heat of condensation will be released, and there will be expansion of air in this column, and as a result the pressure at the center will fall, and pressure gradient force here will increase, and again more and more you see if the circulation increases, then more and more winds will the right hand thumb rule, if you remember, if you have anti-clockwise rotating winds, then the winds this will have like the winds will move upwards. So if you don't have the relative humidity in the middle levels, then this kind of mechanism cannot be sustained. So for the development of a cyclonic circulation, one condition is that we should have relative humidity more than 50% in the middle levels, because it releases because the latent heat released further leads to the evaporation, and it leads to the expansion of the air, the fall in the pressure at the center, and so on. The process continues. This I have explained through this flow diagram, that we have a cyclonic circulation at the center, and then this leads to secondary circulations, and then these secondary circulations lead to release of latent heat, and then there is expansion of the air in this column, and this further decreases the this increases the cyclonic vorticity at the surface, and the process continues. So this is conditional instability of second kind. However, there are certain limitations to this. So those like it does not explain the mechanism of exchange of moisture and energy from the surface of ocean to the atmosphere. For that, another theory was proposed, and that is wind induced surface heat exchange mechanism, WISH theory. And it explains that the stronger are the winds at the surface, and the greater will be the exchange of moisture and the energy from the surface of the ocean to the upper levels, and then greater will be the circulation. So these are the two mechanisms that are utilized to explain the flow of the exchange of energy from ocean to the atmosphere and back to the ocean. Next comes the life cycle of a tropical cyclone. So, life cycle of a tropical cyclone is like there are various categories. The formative stage discusses the development from low pressure to depression to deep depression and cyclonic storm stage. And then comes the immature stage. In the immature stage, further organization of cloud mass takes place, and this is the stage when peak intensification is reached. This is the stage when the pressure at the center falls to the minimum, and in this stage, the winds, the clouds, and precipitation pattern, they all become more organized. And in the immature or the developing stage, you have like all the the patterns, the cloud is nicely organized, and this is the stage when you have maximum intensification is achieved. And once it has developed, in the mature stage, what happens is it is only the size of the storm that is increasing. No further intensification will be observed in the mature stage. And here you have maximum winds are observed in the right forward sector, and maximum rainfall is observed in this in the right forward sector. And decaying stage comes when the system enters into an unfavorable environment. And by unfavorable environment, I mean if it enters into the land, then the supply of moisture is cut off. And or if it enters into a region where the wind shear is very high, or if it moves to higher latitudes, or if there is another system developing within its vicinity, then it may interfere with its intensification. Or if there is cold dry air entrainment into the core of the system. So all these are the parameters that lead to the decay of the tropical cyclone. And over the North Indian Ocean, if you see, the average life period of cyclone is about 5 to 6 days. Then comes the various cyclogenesis parameters, and cyclones they develop over the warm sea area, and they develop because of the interaction between the oceanic surfaces, ocean and the atmosphere. And if you consider the thermal parameters, then we should have high sea surface temperature, normally more than 26 degrees Celsius, and then we have a positive ocean thermal energy more than 50 kilojoule per centimeter square. That is, we should have sea surface temperature more than 26.5 degrees Celsius within certain depth of about 50 meters. Then relative humidity, we should have more than 50% up to middle levels. Then there should be conditional instability of second kind in the atmosphere. Then if you consider the dynamic parameters, then cyclones normally they do not develop near the equator, and you should have like minimum Coriolis parameter is required for development of that cyclonic circulation. There should be positive vorticity at the surface, and then the wind shear it should be low to moderate, about 5 to 10 or 10 to 20 for development of for genesis to take place. And if you see this figure, then here we have explained uh, normally around like over the north in the northern hemisphere around 17.5 degree latitude we have like this is the favorable latitude for development of systems. And globally if you see around 15 degree, this is the favorable latitude. And next comes these are various factors that affect the genesis and intensification. So cyclones, as you know, they develop over the warm sea surface area, so high sea surface temperature exceeding 26 degrees Celsius, and there should be deep thermocline, the depth up to which the temperature is 26 degrees Celsius, it should be more about 50 meters. And then there should be a positive low level vorticity, there should be some circulation or some disturbance at the surface. And then there should be instability in the atmosphere, and then relative humidity should be high in the lower and the middle tropospheres to carry out that mechanism, the conditional instability of second kind, where latent heat of condensation released will further evaporate the air and lead to the development of the system. And then the wind shear it should be low to moderate for the system to sustain. And cyclone, if you consider an engine, if the exhaust is blocked, then the engine cannot start. Similarly, here we have some energy, it is building up. So in the upper levels, there should be some exhaust mechanism to release that energy. So in the upper levels, there should be outflow or divergence for that for the system to maintain its intensity and genesis to occur. Next is the parameters that are responsible for weakening and intensification. This we have already discussed. For intensification to occur, the relative vorticity should be it should increase. Then there should be the upper level divergence should increase. Then wind shear should decrease. Sea surface temperature should be high. There should be strong inflow, and then there should be high relative humidity. And for weakening, if the system enters into land area, or if it enters into an unfavorable environment, means that colder sea or dry air intrusion or wind shear is high, or the outflow is suppressed, in such situations the system weakens. Next comes the about the movement. And movement, you if you see the cyclones are like cork in the ocean, and they are normally steered by the environment in which they are embedded. And apart from that, there are certain other effects that describe the movement of the storm, and that we'll discuss one by one. This is the role of environmental scale forces. And normally, if the system is a depression or a deep depression, then its vertical extension is not much, and it is steered by the flow up to middle level in which it is embedded. And if the system is very intense, extending up to 200 HP levels, then it will be steered by the mean flow between the lower levels, the 850 up to the 200 HPA levels. Then comes the effect of the beta effect. Beta effect explains the role of the latitudinal shift on the movement of the storm. And here, if you see, you have if the parcel of air is moving towards the pole. Uh, First, let me explain this equation. You have local vorticity change as sum of Earth relative vorticity and the planetary vorticity. This term explains the contribution due to the change in the latitude of the place. And if the latitude is increasing, that is, if the system is moving northwards, if latitude is increasing, then the Coriolis term, the 2f 2v sine phi, that sine theta term, that will also increase. As a result, the impact of this term, planetary vorticity term, it will increase. But net vorticity has to remain conserved. Therefore, it will lead to the development of a anticyclonic vorticity over the region. But if you see the left hand side, here, as the system is moving towards the equator, the latitude is decreasing. Decrease in latitude means the planetary vorticity term, which has the component sine of theta. So that is decreasing. This term is decreasing means this term should increase. Increase in vorticity means development of an area development of an area with positive vorticity or cyclonic vorticity. As a result, if you see, you have development of vorticity, negative and positive vorticity gyres around this system, and this will lead to, like, if you imagine the dipole kind of situation, then it will lead to finally northwestward movement of the system. So this is the reason that normally over the North Indian Ocean region, these cyclones, they tend to move northwestwards, but sometimes they recurve also, and that recurvature depends on various factors, depending upon the position of the ridge, depending upon the anticyclone, or depending upon some westerly flow that is approaching the system. So all these parameters also affect the movement of the system. Next comes the Fujiwara effect, and it was given by Dr. S. Fujiwara, and he found that systems which are located within 20 degrees, they have the tendency to interact with each other, and they tend to move in an anti-clockwise direction in the and if you see, if one of the system intensifies, then the other will weaken. And we may have systems developing across the equator, like one in the North Indian Ocean and other in the South Indian Ocean, so they also interact with each other. Or we may have two systems, one over the bay and another over the Arabian Sea. They may also interact if the distance between them is within 20 degrees. And in recent years, like we have not over our region, it is not observed much. One reason is that we don't have much of cyclones, and but we have seen simultaneous occurrence of cyclones during recent years, like Titli and Luban. So there are cases when simultaneously occurring systems have been observed. Next comes the trochoidal motion. Trochoidal motion results because of various kinds of trochoidal means the zigzag motion, and if you remember the structure of the storm, then you have the eye wall, the outer rain, the storm. The spiral bands and the outer storm area, and you have updrafts, downdrafts going on. So all these like they are interacting with each other, and because of that interaction, if you see, a zigzag kind of motion is observed, and this kind of zigzag motion can be observed only through radars, because we are getting hourly updates from radar. But to the general public, we do not give this kind of information. To them, we give a smoothened track only, because they may have a feel that the system is recurving. So these are some of the forces that affect the movement of the storm. Next comes the difference between the tropical cyclones and the extratropical cyclones. And tropical cyclones, if you see over our region, they develop over the tropical region from equator to 23 degrees. And the extratropical cyclones, they develop in the mid latitudes. And the tropical cyclones, in case of tropical cyclones, the strong winds, they are observed near the surface. However, in case of mid latitude cyclones or the extratropical cyclones, you observe the stronger winds in the upper troposphere. And so like tropical cyclones, they are more disastrous as compared to the extratropical cyclones. And if you see other differences, then tropical cyclone, the extratropical cyclones are the frontal systems, and they are the cold core systems, while the tropical cyclones, they are the warm core systems. The core is warmer in case of cyclones, tropical cyclones, as compared to the surroundings. Then comes the difference between the tropical cyclones and the tornadoes. Then this is the typical tornado picture, the figure on the left, and both are very intense systems. But tornadoes, the tropical cyclones, they are synoptic scale systems. But if you see the tornadoes, they have the diameters of about 10 to a few hundred meters, and they are basically produced by severe thunderstorms. And like here, you don't require any strong large relative humidity in the up to middle levels, as it is required for genesis of tropical cyclones. And this is the only difference. Both are equally intense systems. And normally, over our region, we have recently, during prior to cyclone Yas, a tornado was observed over the West Bengal region. So if you next comes the impact of climate change on the various features of tropical cyclones. And here we have summarized the impact on the genesis frequency. And if you see the global trend, then there is increase in the frequency of high category storms, category 4 and 5, due to as a result of the climate change. And over the North Indian Ocean, if you see, then there is increase in the frequency of extremely severe category storms and above. Over the Arabian Sea and over the Bay, no such trend is seen. And if you consider the frequency of landfalling cyclones, then over the North Indian Ocean, the frequency of both category, the cyclonic storm and above category and the severe cyclonic storm and above category, both show a decreasing trend during the period 1965 to 2019. And globally, if you see, then frequency of landfalling TCs, intense category storms, it is increasing, and that of less intense category storms, category 1 and category 2, it is decreasing. But over our basin, the frequency of both the weaker category storms and the stronger category storms, both are decreasing. Next comes the annual frequency of landfalling cyclones. So this, if you see, then overall, over the Bay of Bengal region, the frequency of landfalling cyclones has decreased in recent years. And but if you see the condition over the Arabian Sea, the frequency has increased, and that too, if you see the frequency of landfalling TCs over the Iran and Arabian Peninsula region has increased, and not over our west coast. So the frequency of landfalling TCs over the west coast is the same, but over the east coast, if you see, decreasing trends are seen. More prominent is in case of the less intense cyclonic storms category. Next comes the latitude of maximum TC intensity. global trends indicate that there is gradual shift towards the pole. But if you consider the trends over the North Indian Ocean, this is based on the data during 1982 to 2020, and these trends indicate that there is equatorwards shift of genesis, the latitude of maximum intensity storms. Next comes the propagation speed. So global trends indicate that the propagation speed is decreasing, and over the North Indian Ocean also the average translational speed is decreasing. And if you consider basin wise, then over the Arabian Sea, it is not significant, but over the Arabian Sea, Bay of Bengal, the decrease is significant, and this makes the east coast further vulnerable. If translational speed is less, then definitely it will have more impact over the coastal areas. Then comes the total number of CD days, total number of cyclonic disturbances days. Then they are overall, if you see, North Indian Ocean is indicating increasing trend, and Arabian Sea is also indicating increasing trend. Then comes the track length. Track length also, the systems over the Bay of Bengal, they are indicating increasing trend. And so increasing trend is also seen over the NIO overall, but no significant trend, such trend is seen over the Arabian Sea. Then comes the our services. If you see, we provide cyclone warning services not only for the Indian coast but also for 13 member countries bordering the Bay of Bengal and the Arabian Sea region. And IMD has been designated as one among the 6 RSMCs worldwide. And apart from that, we also provide severe weather guidance to 9 member countries, starting from Thailand, Myanmar, Nepal, Bhutan, Sri Lanka, Maldives, then Pakistan. And then we also provide South Asia flash flood guidance. And apart from the guidance for the coastal population, we are also providing the advisories and guidance for the marine marine community and for sea area. We provide support under Global Maritime Distance Safety Support System also for the ships plying in the deep seas. And apart from that, IMD also plays a crucial role in building capacity in the region. And MTI Pune is WMO's recognized center for training. And similarly, Pune office is also the regional climate center. So we have established our regional leadership in this regard. And if you see the death toll, then during since 2010 to 2020, if you see over the Indian coast, the death toll has reduced significantly. We had witnessed death toll amounting to about 10,000 during 1999 over West Bengal, then during 1971 over Andhra Pradesh. So but during recent years, if you see, the death toll has reduced to less than 100. And not only over the Indian coast, if this is the statistics for the member countries of WMO panel. And there also, if you see, the death toll has significantly reduced. So how it happened? uh, for that, it happened because of very meticulous and scientific planning. And the government of India, it planned national cyclone risk mitigation project. And then modernization of IMD was also initiated, and the Ministry of Earth Sciences was established in 2007. And all these efforts, they addressed all the components of early warning system, including augmentation of observations, then having a decision support system, then warning dissemination mechanism, and development of SOPs, development of high power computing systems, etc. And this is the observational network of IMD. We have today support from INSET 3D and 3DR, and we are getting satellite observations every 15 minutes. And this is our observational network. We have about 56 RSRW, then 560 surface observatories, 20 buoys, 34 high wind speed recorders along the coastline, then 62 pilot balloon stations, then a large array of automatic weather stations and automatic rain gauges, and 33 Doppler weather radars countrywide. And if you see, almost all the entire coastline is covered, and plan is to further augment the Doppler weather radars in the country, and by next 2 to 3 years the number may rise to about 60 to 65. And then in terms of modeling capacities, we for monitoring and prediction of the track intensity, the landfall, and the associated adverse weather with the system, we follow around 10 to 12 different types of models. And in terms of modeling capacities, we are second to none, and we have the capacity of about 10 petaflops, and we can run about 7 to 8 different models that are capable of generating forecast for next 10 days. Twice a day we can run, and we have a very high end decision support system at IMD headquarters, and it like all the observations, it has the facility to analyze all the observations at one platform, and various model products are also available on this platform. And then utilizing these observations and the model guidance, we can generate the forecast, and we can generate the user specific like graphical products associated with cyclones. And then we have a very high end warning dissemination system also. We utilize all modern means of communication apart from the conventional means that we have been using. And we have our mobile apps, then we have specific websites also for this purpose. And this is the entire cyclone warning process. We have a seamless flow. We start with genesis forecast, then we provide extended range forecast for next 15 days every Thursday, and then this is followed by medium range forecast issued for next 5 to 7 days, and this is issued every day. And then once the depression forms, then the frequency of bulletins increases, and 6 hourly observations are shared with the media and the general public and disaster managers. And when it becomes a cyclone, then further the frequency increases and 3 hourly bulletins are shared. And on the day of landfall, we provide hourly updates. And with respect to information, we are providing the information about the track, intensity, structure up to next 5 days, and then landfall point and time with a lead period of 5 days. Along with that, we provide information about the associated adverse weather like the strong winds, the heavy rainfall, and the storm surge. And then the damage expected and action suggested is also provided to the general public and disaster managers. And in this regard, we are providing sector specific bulletins. For the coastal population, 4 stage warnings are issued, and for the marine community, different kinds of bulletins are issued as per their requirement, including the sea area bulletin, the coastal area bulletin, the bulletin for Indian Navy, then port warnings, then warnings for fishermen, then the advisories for fisheries officials, then warnings for aviation, then specific format of bulletin is there to provide information to All India Radio and to Darshan. So this is our mechanism. Next comes the skill in forecasting. So if you see our 24-hour forecast error is 73 kilometers, and 48 hours forecast error is about 106 kilometers, and 72 hours forecast error is about 144 kilometers. And quantitatively, if you see, about there has been a decrease of about 25% in the track and intensity forecast errors during recent years, and 45% decrease in the landfall point forecast error. And in terms of forecast accuracy, I just want to share with you that we have the National Hurricane Center as our benchmark, and our errors are comparable to National Hurricane Center error for Atlantic. And in terms of services, similar kind of services we are even providing a pre-genesis forecast. That is, from the stage of low pressure stage, we are providing the drag and intensity forecast. That service we have started in 2022, and this is the 5-year moving average track and landfall point error forecast. And you can see that there is a significant decrease in the forecast errors over these years. And this is the success story. All these meticulous planning and efforts, they have earned appreciations to IMD, and we have received appreciations from global community worldwide. And
Ma'am,
uh,
actually, next faculty is waiting.
okay. So that's all from my side. So if you have any questions, you can ask. Shall I stop sharing?
Yes, madam.
Yes, please.
Or any questions? You can
I
write
have
in chat box also.
I have already shared the PPT with the organizers, so I think that will be shared with them. And I have written the popular questions also there.
I thank Dr. Monica Sharma madam for an excellent and informative lecture. I hope the audience will be able to create interest in their mind regarding the topic, and they may be feeling free to ask anytime. They may contact for with their queries to madam. So I thank once again for a very good lecture.
Thank you, sir. And thank you, everybody, for very patient hearing.